All right, we're looking here at polynomial functions, their graphs and inequalities. Couple of things, and this is mentioned here in this beginning part, is all polynomial functions have a smooth and continuous graph. And it says by smooth we mean only rounded curves, no sharp corners. By continuous we mean no breaks, and we can draw it without lifting up our pencil. First thing here, it says if the factor x minus c occurs k times in the complete factorization of the polynomial, then c is called a root with a multiplicity of k. Root is another word for like x-intercept or solution or zeros. Those all mean the same thing. If p of x is equal to 0 is a polynomial equation with real or complex coefficients and positive degree n, then when the multiplicity is considered, p of x equals 0 has n roots. So it's basically just saying the degree is going to tell you how many solutions or roots or x-intercepts that particular polynomial has. Right, now, talking about this multiplicity, all right, that multiplicity can tell us what those roots or those solutions or those x-intercepts are going to do as they get to the x-axis. So we say if the multiplicity is an odd number, then the graph is going to cross at that x-intercept. If it is an even number, then it is going to touch the x-axis at that x-intercept. So we're going to look at a couple of examples here on finding some x-intercepts and then being able to determine their multiplicity and then what's the behavior at that at that particular x-intercept. So for this first one here, they have got it completely factored for us already. So all we have to do is take each of those factors and take them equal to 0, and we will solve for x. So we get x equals 1, and we get x equals 3. Now, for the 1, its multiplicity, and I'm just going to abbreviate here. All right, the multiplicity there is a 2, right, because that's the exponent. A multiplicity of 2 is an even number, so that means that it is going to touch the x-axis at x equals 1. It's going to touch the x-axis at x equals 1. Right, for x equals 3, this is an understood 1 for the exponent there. So that means the multiplicity is 1. 1 is an odd number, so it is going to cross the x-axis at that particular solution or that particular x-intercept. Okay, for b, it is not in factored form, so first thing we need to do is factor it. First thing I notice is that it has a greatest common factor of x, so I'm going to take that out. And then I believe what's left behind is a quadratic that we can factor doing slide and divide. So for this particular one, we'll need two numbers that when we multiply them we get -3, and when we add them we get 2. And I believe that would be 3 and -1. So it's going to be x plus 3 and x minus 1. And now that it's completely factored, we'll take each of those factors and set them equal to 0. So the first one's just going to be x equals 0. Second one, x plus 3, and then third one, x minus 1. This is going to make x plus 3 is going to be x equals -3. X minus 1 is going to be x equals to 1. If I look at the exponent of each one of these factors, all right, on this x, that's a 1. On the x plus 3, that's a 1. And on the x plus 1, or x minus 1, that's also 1. So they all have a multiplicity of 1. Right? All of them have a multiplicity of 1. So that 1 is an odd number, so that means they are all going to cross the x-axis. Right? I would encourage you to try C and D, all right, just to give you a hint to start out with. You both need to be factored, and once you get those factors, set them equal to 0. and then go into Moodle and check the answer key to see how you did on those two. Next thing we have leading in here is talking about the end behavior of different polynomial graphs. So to be able to decide end behavior, right, we're talking about the highest degree of the polynomial, so the highest exponent. We're going to be looking at that term, right, and based on that term, so it'll look something like this, all right, so it'll have a number in front typically, and it's going to be raised to some power, all right, and that n is going to be the highest one that you see in that polynomial. Right, you're looking at, for the first part here, is that number in front, which is the leading coefficient, is that number a positive or a negative? All right, that's going to be part of what we're looking at. The second thing we're going to look at is this exponent here. Is this number an odd or an even number? Because that's going to be the second part that determines our end behavior. So looking at the first scenario that you see here, we have, it says a sub n is greater than zeros, meaning it's positive. So if we have a positive number in front, and then we're looking at an odd degree, so positive and an odd degree, notice that you have the ends of your graph. The one on the left is pointing down, the one on the right is pointing up. If for end behavior, we're describing what the x's and y's are doing from the left to the right. So on the left-hand side, our x's are always going towards negative infinity. Now, because on that left side of this first graph here, it is pointing down, that tells me the y is going towards negative infinity. On the right-hand side, our x's always go towards infinity. The arrow on that graph is pointing up, which tells me that my y's are going to infinity. If I look at the next scenario, where a is negative number, and we'll still look at it with an odd, so a negative a and an odd. Right, notice here on the left, the arrow is pointing up, and on the right, it is pointing down. So as we go to the left, our x's still go to negative infinity, but because that arrow is pointing up, that tells us the y's are going to infinity. On the right-hand side, our x's go towards infinity. The arrow is pointing down, tells us our y's go to negative infinity. Right, now let's look at that case for the evens. So if we have a positive number again, so positive number and an even. Positive number and an even. Right, in this case, notice that both of the arrows are pointing up. Right, both of the arrows are pointing up. So starting there on the left-hand side, again, our x's on the left go towards negative infinity. It's pointing up, so that tells us that the y is going to infinity. On the right-hand side, our x's go to infinity. Because the arrow is pointing up, our y is going towards infinity. Right, and our last scenario here, if we have a negative number and an even, so negative and even. Right, look at this graph and you notice both of the arrows are pointing down. So let's start there on the left. Again, on the left, our x's go to negative infinity. If it's pointing down, that tells me that the y is going towards negative infinity. On the right-hand side, our x's go to infinity. The arrow is pointing down, telling us our y's are going towards negative infinity. So that is our end behavior for each of those scenarios. Right, depending on, is the number in front positive or negative, and is that degree an even or an odd number? All right, so let's take a look here at example 2. We've got A and B, looking at some deciding what their end behavior is going to be. So I'm looking at these two terms in letter A. The highest or the biggest exponent I see there is the one that's x to the 4th. The number that is in front is understood 1. that is a positive number. Then if I look at the 4, 4 is even. So I have a positive and an even. Right, that goes to the scenario that we have over here in orange. Positive and even tells me that both of my arrows are going to be pointing up. So my end behavior on the left is going to be x is going towards negative infinity, pointing up for the y is going towards infinity. On the right hand side, our x's are going towards infinity. My arrow is pointing up, telling me the y is also going towards infinity. Right, I would encourage you to try B and see if you can get it correct, and go into Moodle and you can check your answer. All right, last little bit here talking about graphing a polynomial function. Right, so a couple of things you need to be able to do to graph it. You need to have all of your real zeros. You need to determine the behavior at those zeros. So are they going to be crossing or touching? You're going to determine your end behavior. So what are the ends of the function doing? Are they both going up, both going down, going in opposite directions? Then it says calculate several ordered pairs, including the y-intercept, to verify your suspicions about the shape of the graph. And then use the fact that the number of turning points of the graph is n minus 1, where n is the degree. And then draw a smooth curve that goes through those points. All right, so let's see. Starting out with finding those x-intercepts. All right, let's see here. I'm going to go into the calculator, and I'm going to type that function in. So it was x to the third minus 5x squared, whoops, x to the third minus 5x squared plus 7x minus 3. All right, now I could go look at the graph. Right. Right, and you can see there where it is crossing the x-axis. You see it has 2 points, but the easier way would be to look at the table. So if I hit second and the graph button, right, I know that they're going to be x-intercepts if they have a y-coordinate of 0. A y-coordinate of 0 tells me that it's going to be an x-intercept. So I can see there that I have one that's at 3, 0, and I can have one that's at 1, 0. So I have 2 x-intercepts that I know of, 1, 0 and 3, 0. So x equals 1 and x equals 3. For part 2, determining the behavior, all right, as we saw in the graph, for x equals 1, that it touched. And for x equals 3, it crossed. All right, we saw that in the graph in the calculator. Determining the end behavior, all right, the highest exponent I see is on the term that has the x cubed. All right, this is an understood 1, and this is an odd number. So we have a positive 1 and an odd number. In that case, our ends on the left go down and on the right go up. So that tells me as x goes to negative infinity on the left, the y is pointing down, so it's going towards negative infinity. And on the right hand side, x's go to infinity, the arrow is pointing up, so the y is going towards infinity. And so that's how I know what the ends are going to be doing. All right, part 4. We're going to calculate several ordered pairs, including the y-intercept, to verify our suspicions about the shape of the graph. So starting with the y-intercept, the easy way to find the y-intercept is plug in 0 for x. Plug in 0 for x, and that's going to give you the y-intercept of any function. Plugging in 0 for that x. And so all of this simplified, that's going to be 0, 0, 0. So we end up with -3. So our y-intercept is the point 0, -3. Right, kind of continuing with that to find some other points, making kind of a table of values here. All right, we've got a few already. We know that we've got an x-intercept of 1, 0. We've got a y-intercept of 0, -3. We've got another x-intercept of 3, 0. If we picked a couple of points, maybe we also try like 2 and 4. I'm just choosing some other x values. All right, I could easily plug each of those in to see what we get. So we'd have 2 to the third is 8 minus 5 times 4, so minus 20. So 8 minus 20 is going to be -12, plus 14 is 2, minus 3 is -1. You do the same thing for 4, plug it in. So 4 to the third is 64, minus 5 times 16, plus 28, minus 3, I think we end up with 9. So that gives us some points there that we can graph on our graph and figure out what this kind of looks like. Part 5 was to determine the number of turning points. So this is how many like maxes and mins you're going to have. So it says that the number of turning points for the graph is n minus 1. So n is the degree. This highest degree of this function is 3. So if I do 3 minus 1 is 2. That tells me this graph's going to have 2 turning points. 2 turning points. All right, so now that I have all this information, now I can draw my graph, plot the points that I have and graph it. So I have 1, 0, 0, -3, 3, 0, 2, -1, and then 4, 9. All right, and now it's also important probably to go back and remember that this is what the ends of the graph are going to look like. The one on the left is going to be going down, so down this way. The one on the right is going to be going up. So basically, now that I know that, I can just take and kind of connect that together going through those points that we graphed. So there's kind of a general idea of what this is going to look like. All right, so that was a lot of information about polynomial functions and their graphs. The last part of this section, which kind of goes into section 2.7, is going to be looking at polynomial inequalities. Right, so being able to solve them and decide, where are the regions that are true. So solve by finding all the roots or zeros and testing values similar to how we tested them for quadratic inequalities. All right, so let's see. First thing I see is that I need to get this, have a 0 there on the right hand side. So I'm going to move that 15 to the other side by subtracting it. All right. This one is quadratic, which is also a polynomial as well. All right, so this is kind of lead us into looking at polynomials specifically. Now that I've got it all on one side, I can factor it. I can do slide and divide here. So that's going to be -30. So we would need two numbers that we can multiply together to get -30, and we add them when we get a +1. I believe that would be 6 and -5. We need to divide each of those by 2, which was that leading coefficient. So that gives us x plus 3 and 2x minus 5. We could solve each of those for 0. So solve for x, setting them equal to 0. So we get x equals -3. And x equals 5/2. So we're going to come in here and draw ourselves a number line. And we're going to put those two values up there, so -3 and 5/2. And then we've got to choose a number in each of the regions to test to see where it is true, where it is false, because that's going to help us decide what this inequality looks like. So in this first region here on the far left, I need to pick a number that is less than -3. So I think I'm going to try -4. So I would take -4 and I would plug it in to the inequality, that beginning part, and see if it is true or false. So let's see, 2 times -4 squared plus -4. We're trying to test, is it greater than 15? So let's see, -4 squared is going to be 16 times 2 is 32, minus 4 is going to be 28. So yes, this one is true. 28 is greater than 15. All right. In between -3 and 5/2, I need to pick a number that's in between those. Easy one to pick would be 0. So again, we'll test 0. Plug it in. We're going to see. So 0 squared is 0, times 2 is 0, plus 0 is 0. 0 is not greater than 15, so this one is false. And then the last one, 5/2, which is like saying 2.5. I need to pick something that's bigger than 2.5, and maybe I'm going to test 3. So we'll do 2 times 3 squared plus 3. We're trying to test, is that greater than 15? So let's see, 3 squared is 9, times 2 is 18, plus 3 is 21. 21 is indeed greater than 15, so that one is true. So you can see we have true regions on the left and on the right. So I'm going to shade in those regions, because the way they were true. You're going to always shade in the regions that are true. Now, as far as endpoints go, this inequality did not have an equal to sign, so these circles are going to be open. Okay, and then to write my answer in inequality form, or not inequality, in interval notation. All right, on the left, it continues going, which is towards -infinity. Then we come up to -3 with a parentheses because it's an open circle, union. Then we skip until we get to 5/2, and it continues to go to the right, which is towards infinity. All right, 5/2 also has a parenthesis because it is not equal to. I'll leave B for you to try on your own, and you can always go into Moodle and check your answer with the answer key. And let's look at this last one together. Example 5. This one is actually a polynomial. Now the first one was a quadratic, which is a polynomial, but it was specifically just quadratic. All right, looking at this one here, it is already factored for us, which is nice. So to figure out my values, my x-intercepts, I'm going to set those factors equal to 0. I'm going to get x equals 1 and x equals 3. I'm going to draw myself a number line, and I'm going to put those values on it. So I have 1 and 3. And just like last time, we're going to find parts of this to test. So first I need to pick a number that is less than 1. All right, I could choose -1. I have to pick a number in between 1 and 3. Really the only one there is 2. And then I have to pick a number greater than 3, and maybe I chose 4. So we're going to do a test on each of these to decide if they're true, to help us decide where this interval is located. So let's start with -1. I'll plug in a -1, and we're going to simplify it. We're trying to test, is it less than 0? So that's going to be -1 minus 1 is -2. Squared is 4. -1 minus 3 is -4. That's going to be -16. And -16 is indeed less than 0, so that one is true. We're going to test 2. So plug in a 2. 2 minus 1 is 1. 2 minus 3 is negative 1. That's going to be 1 times negative 1, which is negative 1. And negative 1 is also less than 0, so that one is true. And then let's test 4. Okay, 4 minus 1 is 3. Squared is 9. 4 minus 3 is 1. 9 times 1 is 9. 9 is not less than 0, so this one is false. So remember we said we shade in the regions that are true. So I'll shade here. And I'll shade here. Right, and then we got to figure out, this one again did not have an equal to sign, so at these particular points they are both going to be open circles. So if we're writing our interval, we're going to have from negative infinity, starting on the left, negative infinity up to 1 with a parenthesis, union. We pick up on the other side of 1 and we go to 3. Right, and all those had parentheses because none of them were equal to. Right, this completes the notes for 2.3 and part of 2.7. Right, again, please do the ones that I didn't do with you and try to see if you can do them on your own and test, and then check your answers on the answer key in Moodle.